questions, needs, concerns before we get started? Science, physics is all science. Go ahead.
Why does oxygen explode?
Well, it combusts, and combustion can be explosive at times.
Depression.
Yes, actually. The way that I'd try to describe it is most gases that can combust, once the reaction starts, it begins creating a lot of heat. And depending on where the reaction is happening, like say inside of a sealed vessel, the more heat is produced, the more the gas in general, doesn't even have to be oxygen, wants to expand. And so the explosive part is usually just massive expansion because of heat.
It's like an increase in entropy, right?
Yes. Very much so. Explosions are very chaotic. Does that answer the question? Any other late night thoughts for Monday morning? All right, let's see. Devices make noise sometimes, it's fine. I was just like, that felt loud enough that I thought there was speakers making that noise. This room has them, they just aren't great. Wait, do we have them? This room used them? Oh, thank you. One place I never looked. Alright, so on Friday, we began chapter 6 by discussing collisions in general, but also by defining momentum as our newest variable. To briefly review, momentum is a measurement of how difficult it is to stop an object that is in motion. If something has a lot of momentum, it's very hard to stop because it is either moving very fast, has a lot of mass, or possibly both. If something has no momentum, it means it's very easy to stop. Perhaps it has no mass and therefore offers no resistance. Perhaps it also just isn't moving. Those are the only two ways something has no momentum, either no velocity or no mass. So technically light doesn't have momentum, even if it is the fastest thing in the universe. And we're going to be considering momentum primarily through the lens of collisions. The idea that within a collision, within a process where two objects will physically interact in such a way that energy is exchanged, momentum is exchanged, they exert force on each other, causing acceleration. In such an interaction, kind of like how total energy is always conserved throughout a process, total momentum is also always conserved throughout a process. However much there is in a system before something happens, that is true after the fact as well. And we did at least one example where, say, we fired an arrow at a log and tracked the momentum through from start to finish. The arrow had momentum that then had to share with the log once they combined. Looking at that example as justification for how the momentum is conserved from start to finish. And we ended with a very brief look at how momentum is conserved even in places where it doesn't look like it is. The example I gave is noise ahead. The example I gave was golf ball hit wall. If the wall does absorb momentum, why doesn't it move? It's because the wall is so massive you don't notice it moving. So that's one of the cases where momentum is conserved even if it doesn't look like it is. But there's another pretty common case that I want to kind of start today off with. Another scenario where momentum is conserved, I promise it is, even though it might not look like it is. It's kind of actually apt that you mentioned explosions. So thank you for that. One of my favorite old episodes of Mythbusters was the water heater rocket episode. They took a water heater, disabled all of its safety features, and let it build up pressure until the bottom was overtaken by the pressure and it just shot off into the sky. I'm gonna slightly modify that example and we're just gonna have it blow up. So it's not shooting off, it's just exploding. Before, because every one of our collisions is gonna have a before state versus an after state. In our before state here, how much momentum is in the system? 0, nothing's moving yet. So whatever the mass of this object is, current velocity is 0, therefore momentum initial should be 0. Now our after state, this object is going to be in pieces. And every one of those pieces is going to take off in a different direction very fast. If those pieces are moving very quickly, how much momentum does each individual piece have? You don't have to give me a number, just if they're moving very quickly. Sorry, let me rephrase the question. Each piece, if it's moving very quickly, would you expect it to have a lot of momentum?
Yes.
Okay, now, the weird thing is, conservation of momentum states that there shouldn't be any momentum after this process, right? Initially, all the momentum added up to 0. So in this final state, all the momentum still has to add up to 0. And it technically does. Even if each individual piece of this former water heater has its own individual momentum, the total sum of all the momentum is still 0. And that's because momentum is a vector. If one piece shoots off to the left, another piece shoots off to the right. And their momenta still add up to 0. Because they're vectors. This is technically true of any type of situation that one could call an explosion. In physics, when you're, well, sorry, rewind. Explosion type questions are basically the same as collision type questions, except for a normal collision scenario like we did on Friday, you've got two objects physically colliding, and then whether they combine or bounce away from each other just kind of depends. An explosion question, kind of like this, everything kind of starts at rest, and then all the pieces rocket away from each other. This is true not only of literal explosions, but also of things that kind of somewhat resemble explosions. For example, you might have seen this in a movie, maybe, just maybe. This is a frozen lake, and this guy's stuck. They didn't bring snowshoes. You know, some movie thing has happened, and this person is stuck in the middle of a frozen lake. Can't walk anywhere, it's too slick. So how do they get back to the shore? They start taking all the heavy stuff that they brought with them, and they throw it away from themselves. Initially, person and stuff combined net momentum of 0, right? Nothing's moving yet. But after they throw their stuff, so this is going to be a very poorly drawn backpack. Backpack is now moving that way, and person is now sliding backwards. If you're on ice, you kind of need no friction for this to happen. And you throw something this way, the recoil is going to knock you backwards, right? Does that sound like anything you've seen in movies or on TV or possibly experienced in real life before? Very mixed reactions, that's fair. We don't get a lot of frozen lakes in South Carolina.
It's also like if you're on a skateboard.
Ooh, yes, skateboard. That's better. That's a better example, actually. That's something that exists around here. point is, if a bunch of collected objects, they're like a person with stuff or even one item that then explodes, if the before state everything is at rest and in the after state something is launched away from the rest state, the net momentum still adds up to 0, and it means that whatever was left behind is going to get recoiled backwards. It has to, so that the total momenta of every object still adds up to 0, considering that they're vectors. We're going to do examples for this, so I'm going to help it make sense. But I'm just starting today off with the premise that there's multiple scenarios where the momenta before and after still add up to the same number, even if it doesn't look like they do. In this case, the momentum does kind of spring out of nowhere, but it all still adds up to 0. It has to. And I think there's a homework question that specifically references this type of thing, if you've looked at the chapter 6 homework yet. So, I want to give a new term to kind of help explain why this happens, and then we're going to do an example involving both this explosion idea and also the new thing I'm about to define for you. Because momentum has a second concept attached to it, that is the concept of impulse. There's a few formulas on this slide, but the one I'm looking at right now is down here. And I kind of hate that impulse is treated as its own separate thing, because the definition of impulse is just change in momentum. If an object's momentum changes, usually because it's speeding up or slowing down, gaining or losing momentum, physicists like to say that it has undergone an impulse. So, in this scenario, from start to finish, once all the pieces of this water heater separate and before they rocket off in every different direction, each of those individual pieces undergoes an impulse because initially they have no momentum and afterwards they have lots of momentum. So each single piece has an impulse. The momenta of each piece changes. Impulse is just a fancy way of saying change in momentum. I don't know why we bothered to give that its own name, let alone its own variable. If you see a lowercase j on your formula sheet, that is impulse. Again, physics ran out of letters that made sense a long time ago. So the j is impulse. Call it Jimpulse if you want. Jimpulse and rhomentum to make more sense of your formula sheet. And again, the concept of impulse is just change in momentum. If something's momentum changes, it underwent an impulse. The reason I'm bringing it up here is, again, to point out each single piece of this water heater undergoes an impulse from start to finish. Same with this other type of explosion question. Initially, human and bag have no momentum. Afterwards, they undergo an impulse, and they both have some momentum in opposite directions. I think the reason that impulse is treated as its own separate thing is that there are more formulas for it than just delta rho. Impulse is delta rho. I think the most common way of calculating impulse is just looking at the mass of the object times its change in velocity, because in this scenario, again, this is technically an explosion, even if it doesn't look like it. There's no actual fireball involved. But this is an explosion because the two items begin together and then end up rocketing away from each other. Net momentum still adds up to 0. And if we wanted to find the impulse of each separate entity here, backpack versus human, you can take the mass of each individual and multiply it by its change in velocity. Note that their changes in velocity point in opposite directions, so their impulses will point in opposite directions. Because since momentum is a vector, so is impulse. So the backpack's impulse points to the left, the person's impulse points to the right. But there's another formula for impulse that I'm gonna add here, that's currently on the board. Force times time. Force times time. I mentioned on Friday that a part of collisions is that the items involved are going to exert forces upon each other. Any sort of collision is going to be force between the two or more objects that are colliding. Here, person exerts force on backpack as they throw it away from themselves. Therefore, as a response, the backpack is going to exert a force back on the person. That force is what's going to cause both entities to accelerate. If the person is pushing the bag leftwards, the bag accelerates leftwards. Meanwhile, the bag, as a response, is pushing the human rightwards, so the human accelerates rightwards. And the interaction between the two of them, the collision or the explosion, takes a certain amount of time. The force is only applied for a certain amount of time. There's only a certain length of time to have that acceleration. It's going to determine the speed that they accelerate to in each direction. So, impulse is defined as change in momentum. It means that an object's velocity is changing because a force is causing it to accelerate over time. To tie this back to this explosion concept, each entity here exerts a force back on the other, and the forces last the same amount of time. Because they're applied at the same amount of time, the person's only pushing the bag for 0.1 second, therefore the bag also only has 0.1 second to act back on the person. And the reason I'm talking about impulse with this is to point out that if these two entities exert the same force on each other for the same amount of time, their impulses will be equal but opposite. They have to exert the same force on each other due to Newton's third law. If I throw something with 5 newtons, it's going to exert a 5 Newton force back on me. It has to because of Newton's third law. They'll just be in opposite directions. And the time I'm applying a force, the thing I'm throwing is going to have the same time to apply its force back because the interaction only lasts the same amount of time in both directions. So if we're exerting equal but opposite forces on each other for the same amount of time, this formula tells us that I will undergo an equal but opposite impulse as whatever I'm throwing. And that's kind of why this idea that you can throw something and then get recoiled backwards comes from. Because if you are giving the bag an impulse, if you're changing its momentum forwards, it in turn will change your momentum backwards. You'll undergo the same impulse, just in opposite directions. Your changes in momentum will be the same in opposite directions. And that's why the total momentum of the system still adds up to 0. If I give the bag 10 kilogram meters per second, 10 kilogram meters per second of momentum this way, we share an impulse, it's going to give me, same force for same amount of time, 10 kilogram meters per second of momentum that way. Because we're same force, same amount of time, our impulses will be equal and opposite, and that means that our final momenta will be equal and opposite. That means the system momenta still adds up to 0. I'm doing a lot of hand waving and gesticulating. We're going to do an example to try to solidify this in your minds. How do you guys feel at the moment? Okay. Again, the ice thing doesn't happen much around here, but at least when I was making my notes, what I considered to be a slightly better example of both an explosion and recoil is an over-the-shoulder rocket launcher. So that's the scenario we're going to look at here. It's easier to put numbers to just the person in the rocket in comparison to like every single scattered piece of this shattered water heater. So, changing the picture slightly. We are going to fire a shoulder-mounted rocket launcher. It's still in its testing phase. It's not a very good rocket launcher, as we will find out momentarily. So here's our initial position. Both you, the human, and the rocket are starting together at rest. Nothing's moving yet. So what should the total momentum of this initial system be? Zero. Nothing's moving yet. So velocity initial rocket, 0. Velocity initial human, 0. Total momentum initial for the system, 0. Nothing's moving yet. Nothing's happening. We haven't pulled the launch mechanism yet. Now, we've got the mass of both the rocket and also us. So we have the mass of the two relevant things here. And this rocket is going to be launched forward at 81 meters per second. So we'll do our after drawing now. We're going to launch the rocket forwards. It's moving very quick, as rockets tend to do. And if you've watched movies where these sorts of objects are used, you've probably noticed some amount of what physicists would call recoil. If you launch anything, there's technically an amount of recoil. Even if you just throw something, you feel recoil, because if you exert a force on it, it's going to exert a force back on you in the opposite direction. Throwing does it too, and that's why throwing something too hard can hurt your arm. So, a launcher has to exert a certain amount of force forward on the rocket to make it launch at this speed. Usually this is done by an explosion. And in turn, the rocket is going to be exerting a force back on the launcher, and then by extension, you. If a force launches this thing forwards, it's going to push back on you and kick you backwards as the rocket launches forwards. Does that sound consistent with your expectation of reality so far? Okay. Now my end goal is we want to see if this is a good rocket launcher or not. I want to know the speed at which this person's going to get kicked back at. How fast they're going to be thrown backwards by this prototype launcher. If they get thrown back too fast, it's not a good prototype, and we have to go back to the drawing board. It has to be able to not throw you back 10 feet every time you use it. So that's the main end goal. They want to know the recoil speed, how fast a human of this mass would get kicked back by this rocket launcher by using it. So, first thing I want to do, since I just gave you the definitions for impulse, I want to quickly ask, what is going to be the impulse of the rocket from start to finish in this example?
Also be 0. Right.
Well, impulse is change in momentum.
Yeah, final momentum is 0.
The rocket's final momentum is 0. Well, it's moving at 81 meters per second.
So the initial, or like the system is 0 at the end.
So, impulse, change in momentum. Mass times change in velocity, force times time. So the rocket's velocity is going to change between phases here. Initially, the rocket's not moving. Afterwards, the rocket's booking it. So we are launching the rocket at a its final speed is going to be very fast. In order to increase from 0 to 81, it needs to gain a lot of momentum in the launch sequence. That means its momentum is changing, so it is undergoing an impulse. And looking at the many different ways to describe impulse, mass times change in velocity is one of them. We know both the final and initial velocities of the rocket along with its mass. So we can figure out the impulse of the rocket, how much momentum it gained in this interaction. So, impulse, rocket. Its mass is 15 kilograms, its final speed is 81, its initial speed is 0.
1,250.
Is that, say, 215 or 50?
215.
15.
Ghost.
It's an old campus, we may have ghosts. 1,215.
Kilogram meters per second.
Thank you. If I didn't say it out loud yet, impulse has the same unit as momentum, since impulse is just change in momentum. So they are both kilograms times meters per second. Stay, good dog. Now, both impulse and momentum are also vectors. So what direction does the rocket's impulse point? Rightward, because initially it's not moving, then it is moving to the right. The momentum it gained, the change in its momentum is rightward facing. So, in this yes, sorry.
Is that bottom, J, does that say human?
That says rocket.
Oh, and the top one says rocket as well?
Yes,
Okay,
J rocket equals
Okay,
mass
okay.
times change in velocity, J rocket equals 1215.
Okay, thank you. I just couldn't see.
No, thank you for asking. Please ask. My handwriting is garbage. So, this is the amount of momentum that the rocket gains in this interaction. An impulse is a vector, it's pointing to the right, as the momentum the rocket gains is rightward facing. Its final velocity points to the right, so it had to gain rightward pointing momentum. Now, related question, what will the impulse of the human holding the rocket launcher be?
Would it be the same thing?
Same number,
Reverse direction.
opposite direction, very good. And I'm going to prove how that works. I'm going to prove how that works. We know that the rocket gains this much momentum forwards, and if overall the system's initial momentum was 0, we know this because nothing's moving at first, then an equal amount of backwards momentum has to be generated to cancel that out and keep the system momentum at 0. But I'm going to demonstrate how to find that mathematically and not just assume it. On Friday, we can, sorry?
So you're shooting a rocket at a certain force and it's putting the same amount of force back on you?
Correct. The mechanism exerts a force on the rocket forwards. Likewise, the rocket would push back with the same force for the same amount of time. And if the same force is acting on you, but backwards for the same amount of time, you should have the same, well, an opposite impulse as well.
If you plug it into the mass times change in velocity, would it be different?
Well, the human has a different mass and they're gonna have a different recoil speed, but they should create the same impulse.
I guess I'm confused with recoil speed and impulse.
Oh, sorry, yes. So, To find the rocket's impulse, we used its mass and its change in velocity. The human's impulse would be their mass times their change in velocity, and those would be different numbers. They both start at 0, but the human's gonna get knocked backwards at a different speed and will have a different mass. And what I'm gonna prove to you is that that different mass and that different change in speed is still gonna create the same impulse. That's what I'm gonna show.
Oh, okay,
Does that make more sense?
Yes.
Okay. Now, to get to that point, I'm gonna use this as my starting point. We're gonna analyze the total momentum of the system from start to finish. Initially, we've got momentum initial rocket plus momentum initial human. And afterwards, we've got momentum final rocket, excuse me, plus momentum final human. Now, we've already done the math. We've done the at least mental math to prove that the initial momenta are both 0, because the objects are not moving at first. But I'm not going to fill in that information yet. I'm going to do something a little bit different to try to illustrate my point about the impulse. We know that both of these numbers are 0, because both of those speeds are 0. We can prove that, but I'm doing something a little bit different. I'm going to keep these as they are for right now. And what I'm going to do is, I am going to rearrange this slightly to get all of the rockets information on the left side and all the humans information on the right side. So I'm going to bring momentum final rocket over here. Nope, I'm going to reverse that actually. I'm going to bring momentum final human over here, momentum initial rocket over there. Nope, that should be a minus sign, pardon me. So, rather than there being 2 initials for different objects on one side and 2 finals for different objects on one side, I rearranged it so that each side has the initial and final for each individual entity. Initially on the right, I took the initial for the rocket and sent it over to the right side. Meanwhile, I took the final for the human from the right and sent it to the left, so that the left is initial and final for the human, and the right is final and initial for the rocket. We are mathematically allowed to do this. And this proves that both entities will have the same impulse. Because final momentum minus initial momentum is impulse. That's change in momentum, right? Final anything minus initial anything is change in that thing. So here on the right, we've got momentum final rocket minus momentum initial rocket. That's the rocket's change in momentum. That's the rocket's impulse. And I'll even prove that that works. Momentum final rocket would be its mass times its final velocity. Momentum initial rocket is its mass times its initial velocity. 15 times 81 minus 15 times 0 is 1215. So we rearranged it so that the right side is just the impulse of the rocket. And that leaves the left side as the human's impulse. It's a little bit backwards. This is momentum initial human minus momentum final human. But it's still basically the change in momentum of the human. The terms are just a little reversed. It's actually the negative of the impulse. I'm basically going to try to distribute a negative sign out real quick. I'm distributing out a -1. And that'll switch the signs of the two. Momentum final human minus momentum initial human. I've distributed out a -1, and that's just gonna switch the signs of the two, which allows me to rewrite it as final minus initial. So it's just negative times final minus initial. And this is the part that proves that the human will have an equal impulse, but in the opposite direction. Same number, but negative sign means backwards instead of forwards. Two objects involved in a collision, be it a normal collision or an explosion, have equal and opposite impulses because they exert the same amount of force on each other for the same amount of time. If one of them is gaining momentum, the other had to lose the same amount. Or in this case, they gain the same amount of momentum, just in opposite directions. So the human should have the same impulse as the rocket, just opposite sign. Try to simplify it one more line here. Final momentum human minus initial momentum human is just impulse human. So -1 times J human. The right side, we've already determined is 1215. It's just the impulse of the rocket. Bring the negative over. The human's impulse is -1215 because it points backwards. They have the same magnitude of impulse. They must, so that the overall change in momentum of so that the final momenta of the system still adds up to 0. The rocket gains 1215 that way. Human gains 1215 that way. Add up to 0 still. How's this feel?
Easy.
Yeah? Glad to hear. So, I'll bring this over here just to keep the two impulses written next to each other. Again, showing here, impulse human, same number, but would have to have the opposite sign. So, we got them both written here, same magnitude, but opposite directions. This would be the impulse of the human. And since we know, don't I ask? Well, since we now have the impulse of the human, we can figure out two things. One, since we know the collision time, we can figure out how much force had to make this happen, how much force is involved in the explosion inside of the bazooka. And then two, how quickly backwards this person would be launched if they underwent a 1215 impulse. So for that, we're kind of using every single possible formula for impulse today. Impulse is change in momentum. Impulse is also force times time. The force of the explosion is going to act on both entities for 0.05 seconds. So J equals Ft, 1215 equals unknown force times that many seconds. Force would be 1215 over 0.05. That's going to be a lot of force. There's a lot of gunpowder in this thing.
It's 24,300.
So that means that this thing is exerting 24,300 newtons forward on the rocket and 24,300 newtons backward on the human. This should already be our cue that that is a very poorly designed rocket launcher, because that is more than 20 times what I weigh. That would break my arms if it didn't render them jelly. So already this is not a safe thing to use. We can further prove that it's not a safe thing to use by figuring out the final velocity of the human after they undergo this negative 1215 impulse. I'm running out of board, so I'm going to do it on the other side. Impulse human equals mass of human times their change in velocity. So negative 1215 equals 75 kilogram mass of the human, unknown PF minus the initial speed of 0.
16.2.
Thank you. And it'd be negative just meaning backwards. 16.2?
Yeah.
Thank you. Backwards meaning left in this case. 16.2 meters per second, which is way too fast to be suddenly launched backwards by something. That would take you off of your feet, and within a second, you'd be 16 meters away from where you were originally standing. That's 40 feet? That's too dang fast. So, we've proven this is not a good tool to use ever, and should never be placed in any human's hands. I wouldn't even trust a robot with this.
So
Yes.
if it's always like the same, you know, the rocket going forward on the human, how do they make a stronger rocket and have it not, like a spring maybe?
Well, I will point out, I designed this question intentionally to be very poorly designed if we interpret it literally. What actual, shoulder launchers tend to do is, basically, it's just an open cylinder with, an exhaust vent on the back. And when you load in the rocket, it's basically just being held in the cylinder. There's not actually like much of a back plate, it's just the exhaust vent. So when you fire it, you're just triggering literal rockets inside of the rocket, and they just launch the rocket forward while exerting as little force on you as possible. Basically, you're just holding a tube that the rocket slides out of, rather than like a traditional bullet where there's an explosion that launches the thing forward. It's just being propelled by its own jets over your shoulder without actually having to push back against you. This one, again, fully designed on purpose for me to illustrate the point. Real ones try to avoid this problem. Real ones, basically, you're just kind of a slide for it as it ejects over your shoulder. Does that answer the question?
Yeah, that makes sense.
Yeah, this one, if someone did build something that worked like this, it would basically just be a shoulder-mounted cannon that used an explosion to launch a cannonball. Because technically, again, the way that, for you to get knocked back like this, it would have to be a bomb going off inside of the thing to create that much recoil, rather than, again, the actual bazooka that's just, it's sliding off of you under its own power. So this would really be more, again, of like a cannon from an old pirate ship mounted to your shoulder, where an actual gunpowder explosion goes off inside of it. So don't do that. Assuming you could lift one of those cast iron things in the first place. Unrealistic, but sometimes I make unrealistic examples to help drive the point home. Questions? All right, so main things from today: definition of impulse, change in momentum. If two things are involved in any type of collision with each other, they will have the same but opposite impulse as each other. In a more classic case, like we looked at on Friday, with the arrow hitting the log, in this case, they have the same impulse because however much momentum the arrow loses, the log gains the same amount. In this case, it's more along the lines of the explosion generates forward momentum in one object and the same amount of backward momentum in something else, so that the total momentum is still zero. But whatever type of case it is, impulse across a two-object collision should be the same, just opposite, between the two objects. And that's going to be one of the things we prove in lab this week, because we're back on a normal lab schedule for now. This week's lab is going to involve collisions. Namely, if you remember the air tracks that we used the last lab before the test, you're going to be causing collisions on that. You're going to be launching two carts at each other to see what happens. But that will be investigating not only impulse in the collision and therefore momentum in the collision, it'll also be about the type of collision, because there's multiple types, and also what happens to kinetic energy in a collision. We've been talking about momentum for the past few days, but there is still energy involved in collisions of all types. Because if you have momentum, you have kinetic energy. The two formulas both have M and V in them. I'll just illustrate that real quick. I haven't shown them to you side by side. If you have one, you have the other. Because if you have mass times velocity, you also have 1/2 mv squared. So any collision or explosion that involves momentum, kinetic energy is there too. And as we continue on through lab and the other lectures this week, we're going to start contrasting the two, watching what happens to kinetic energy in a collision alongside the momentum in a collision. Questions, comments, concerns, etc.? All right. Let me know if you guys need anything. Make sure you bring all relevant notes to lab this week, whenever you have that. And have a great day.